Bring the notes up for it. (13.6). So 13.6 is called parametric surfaces and their areas. So remember way back in chapter 10, way back in chapter 10, we said that if we defined a vector function, r of t, to be equal to f of t, g of t, either two-dimensional or r of t is three-dimensional, then this would draw a curve. This would draw some sort of curve or path in either two or three-dimensional space. Right? Okay. So these were the examples that I actually gave you way back in chapter 10. Okay, we have this thing, we let t start going, and we can draw these different paths. We could do it in three-dimensional space, right? So this is all stuff we've seen. Okay, what does it take, though? What is it going to take for us to draw a surface in three-dimensional space with a vector function? Right now, the only way we draw surfaces is using things like z equals, x squared plus y squared. And we know that that would draw like that kind of bowl paraboloid looking thing, right? We can draw a surface, but this is not a vector function. This is an equation. We can draw other surfaces like x plus y plus z equals 10. And that would draw us a plane, wouldn't it? That's a surface. But is there another way to draw surfaces in three-dimensional space, not using equations, but using vector functions? And the answer is yes, we can do it. But what we're going to have to do is, you know how we had r of t earlier? R of t, we had one input. This time, we need two inputs. And then our output is going to be a three-dimensional vector. And if we can construct a function like this, then this will generate a surface in three-dimensional space. Each of these component functions that we have are functions of two variables instead of one variable. And these are called our parametric equations of the surface. So what we're going to start with, because now at this point they start getting into the calculus and you start doing areas of surfaces, but you have no experience right now in taking a surface and writing it in this form. So we're going to use that the handout, to try and take all these surfaces that we may be familiar with and write them in this form instead of the other form. Then we can start doing the calculus, all right? So please have that handout ready. And I have an interactive version of this. So the first example A, we have this disk. Okay, you see this disk? And just for reference, I hope you can see that this is red, green, and blue. So computer science people, RGB, yes? Red, green, blue. Red, green, blue for me is X, Y, Z. So that's our x-axis, y-axis, z-axis, all right? X-axis, y-axis, z-axis. So this disk right here has a radius, it appears to be what? What's the radius of that disk? 2, right? And I would like to draw that disk with a vector function. All right, so what I need to do, or what we need to do, is come up with the vector function of two variables u and v that would draw me just this disk. And it will have three components, three component functions that I need to come up with. All right, so let's talk about this. What's that? Y is 0. Do you all agree that y is 0, no matter what? Because this flat disk, the y-axis goes this way. The y-coordinate, if you're any point on that disk, the y-coordinate has to be 0. So I agree with that. Y is 0. Now remember, we have control over two things. U and v are the two things that we have control over. Just like before we had control over t, u and v, we can set bounds however we want on u and v. But we need to now see if we can't draw the rest of this. So how are we going to draw the rest of this? Like, how do you interpret this disk? There's many ways to interpret this. Sine and cosine, right? Something like that. So could you draw me just that circle right there? What would the equation in like a parametric form of that circle be? The x would be 2 cosine t or something like that, right? And the y would be 2 sine t. And that would allow you to draw that outside one. Okay, so what about this circle? This circle is also in the disk. That has a radius of 1. So that one would be 1 cosine t, 1 sine t, right?
X is greater or less than or equal to?
Yes. How about I just show you this first one, and then once you see it, you'll be like, ah, okay, I see what you're doing. Right, so watch. I know my x coordinate needs to be cosine of like t or something, right? But I can only use u and v. So I'm just gonna use u. Cosine u and sine u. And if I let u right now be between 0 and 2 pi, do you all agree right now that this alone would just draw me that circle right there? Because the radius is 1. I need to visualize that what I'm trying to do is draw all the circles with all the different radii, right, that go between 0 and 2, right? So I have another variable, v. So I'm going to put v in front like that. And then I'm going to let my v be between 0 and 2. Does it make sense to you that this will work? The way you can kind of think about it is this. Let's start by fixing v to be something. Let's let v be 0, all right? And plug in here, what would we get? 0, 0, 0. So that would draw me the origin, wouldn't it? Now let v be a little bit bigger than 0, okay? Just a little bit bigger. Now once we've fixed our v, let's let it be held constant. Let's now let our u go between 0 and 2 pi. So I've got a little number here, cosine of u, little number here, sine of u, and that's going to draw me a little circle, right? So it draws me a little circle. And then I keep letting v move and keep on doing circle after circle. Does that make sense? That should draw you the disk. And if you look at my code for this, if I actually bring up my code that I wrote to draw this, you'll see I'm using something called parametric plot 3D, which is a built-in function here. And right here, I do v cosine u, 0 for the y, v sine u, and then I tell the computer I want u to go from 0 to 2 pi, and I want v to go from 0 to 2, and boom, it draws me this. Right? All right, let's do example B. So for example B, you have to find the vector functions, plural, functions, plural, which yield the four face surfaces of this tetrahedron. So you actually have 4 surfaces here, right? That doesn't want to spin around very nice for me. But you get it, right? 4 surfaces. I'm going to have to come up with 4 separate vector functions to draw each surface. Now, we do need to get some idea of what's happening here with these vertices. So why don't we start with this one? You want to start with the ground? You want to start with the ground? The ground goes here, 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 here. So that's the bottom side of the surface, or the tetrahedron. Let's call that S1, surface 1. So for surface 1, let's talk about what we've got here. What axis can I label this to be?
Yes.
X, and then the other axis I'm working with is Y. Do we know, we have this triangle in here, don't we? Do we know what this point is right here? I think it's 3, right? Because 3, this right here, so 1, 2, 3, this is 4. So that's 3. So this is 3. And do we know what this point is? 4, that's that one right there, right? So this is 4. We want to be able to draw everything in here, right? everything in there. And I want to be able to do it with some surface vector function. So I'm going to call it r sub 1 of uv because I'm doing surface 1. Is there anything you know for sure about this? Something is 0. Z is 0, right? Z is 0 because we're on the ground. And now you have full control over two variables at this point. So what would you like to do here?
We could just set u equal to x and v equal to y, and then
Okay, hold on. You want this, you want x to be our u,
yes,
and you want our v, you want this to be v? Is that what you said? V?
yes.
Okay, and then what would your restrictions on u and v be?
U would vary from u to 3.
You would go from 0 to 3, so this is going to draw this way, right?
Yes.
0 to 3. Y'all buying this? Okay, what about v?
It's from 0 to negative 4/3 u plus 4.
But you want my v to do what?
The v can vary between 0 and negative 4/3 u plus 4.
So why not just 4?
Because that will draw a rectangle.
That would draw a rectangle. Does everyone agree with that? If I let u go between 0 and 3, then it's going to go back and forth. And I let my v go between 0 and 4, it's going to go up and down. So what I'm going to wind up doing is drawing a rectangle. I don't want that, right? I don't want that. So I can't let v be completely unrestricted. V does have to go, the v is the y-coordinate. My y-coordinate has to always stay between here and here, right? No matter where I am on u, I've got to stay between here and here. So the bottom is 0, and the top is this line, right? And that line, if we were to use our y equals mx plus b, the slope of that is negative 4/3 x plus 4, right? That's this line equation. So my v, which is really my y-coordinate, must stay between 0 and that point. That point is that point, but x is not x. X is really u. So this has to be 4, well, that plus, or minus, I'll say. Should have given myself a little more room. 0 less than or equal to v less than or equal to, I'll just write negative 4/3 u plus 4. That's what you had said, right? Okay. I just want to make sure we were all on the same page with where that comes from. Questions on that? If you fix me a u right now, okay? So like right now, let's fix a u. Someone give me a u. Anything between 0 and 3? 2. So if you give me 2, right? You give me 2, I'm going to come out to 2. Then that's, let's do something a little bit easier to work with. How about 0? What if u is 0? Then where are we here? We're over here, right? Now my v has to stay in between here and here. Will it? V has to be between 0 and u is 0, right? So that's going to be 4. So that keeps me between 0 and 4 only when u was 0. So it draws me that line, segment. And as you move across u, you will continue to stay between 0 and that line segment. Is there any other way we could have done this? Is there another vector function we could have used? Let me put it up here and let me see if that is a correct answer, okay? But let me see if we could do it a different way. You tell me whether or not this one would work. Would that work? I'm not using a V, right?
It'd be the same as your substitution.
So is that going to draw me the region?
No,
No, why not?
it only draws a line.
It draws just a line. So look, if you let's pick a U again. Let's let U be 0, all right? Then what's it going to draw? If U is 0, it's going to draw me 0, 4, right? 0, which is going to draw me that point. But notice it's not drawing me everything in between. Do you all see that? Now let's pick another number. Let's pick 3, which is the other end, right? So if I pick 3 for U, that'll be 3. This will be what? 0, 0. That puts me here. And then if we take something in the middle, like U is 1, and you put those together, you have 1 here, and then you'll have some number, you'll be here. So if you do all the U's from 0 to 3 and plug it in, you're going to draw just that. And that's not what we wanted. Do you see the difference between?
Yeah.
So I gave you 3 different vector functions. Only one of them was right. The first one I gave you, we did U, V, 0. U was between 0 and 3, and V was between 0 and 4. And this was incorrect because it drew the entire rectangle. Then we did it the second way, which does it. And then we did it this way, which just draws you the line. So you just have to be real careful. Make sure you understand like what your vector function is drawing. I should already know that this is drawing me a line, because isn't this vector function a function of one variable? So this may as well be like R of t. And R of t draws lines or curves. All right, we've only got one of the surfaces. How about let's do the back surface. We have 2 kind of back walls here. This one, that, let's call it S2. So what axes am I working with this time? The X and the Z. So the X, this was 3, and this one was, what's my Z? 2? It's not drawn to scale, I guess I'll move that down. So we have this happening. This would be very similar to the last one, right? So R2 of UV should be equal to, this time what's going to be 0?
2.
The y will be 0 this time, right? The y will be 0. And the x, I can call that the x. Why don't we let that be the u, right? And then what about the z part? Call that my v, right? And then u must be between 2 things, and v must be between 2 things. So what must u be between? 0 and 3. And then my v has to be this thing, right? So I need 0 to what? So we have to find that slope again, right? Negative 2/3 u plus 2. And we're using u instead of x because the x is u. All right, you think you could get the other side, this back one, S3, you think you get that one yourself? Yep. Yes? Okay, what are we missing? The actual plane that cuts through, that touches these 3 points. So how are we going to get that? This one's the trickiest one.
You have to kind of like do the 2 vectors and then
Yep.
do the whole thing.
Yep.
solving for plane.
So we are going to try right now to find the vector function which will draw this triangle, which is, tilted over. We'll call that S4. So what we'll start with is, like you said, let's put these points here. This was 3, 0, 0. This was 0, 4, 0. And this point here is 0, 0, 2. So what I'm going to first do is find the equation of that plane. Right? To find the equation of that plane, I have to make 2 vectors, cross them, and that'll give me a normal, won't it? So let's create 2 vectors. Here to here, here to here. So we'll just call that, I don't want to use u and v because I'm using them later. I'll call this w, W1 and W2. So what's W1? The vector
Be -3.
-3, 0, 2. And then W2, -3, 4, and 0. And then I'm going to cross these, right? And when I cross these, that'll give me my normal vector of my plane. So when I cross these, let's see, what's the first component? When I do W1 cross W2 is what? -8. And then I cover up this one.
-6.
So this is 0. Minus -6 is +6, but then you have to change the sign. So -6. And then last one, -12. That's a normal vector, right?
Do the plane equation, right?
Now I have to do the plane equation. Now I'm going to choose a different normal vector because my normal vector just has to, it's any vector that's pointed in that direction, right? So I'm going to scale this down. For my normal vector, I'm going to divide everything by -2. So I'm going to use the vector 4, 3, 6. That I can use, right? Because it's just a scalar multiple of this. So my plane equation, the equation of the plane S4 is 4x minus what? We can use any of these points, right? So why don't I use this one? X minus 3, and then plus 3, y minus 0, plus 6, z minus 0 equals 0. Does all this ring a bell like we did this way back in the day? So my plane equation is 4x plus 3y plus 6z equals 12. That is the equation of that plane. Are you with me? All right. I'm going to erase all this. I'm just going to leave the plane equation up there. Because now we need to figure out how in the world we're going to draw S4. So here's something I want you to think about. Take a look at this. If I take a look at S4 from the top, isn't S4 almost identical to S1? Now what was S1? Just so we remember. S1 was R1 of UV was UV0, right? And U was between 0 and 3, and V was between -4/3 U plus 4, right? That was it? That's how we drew S1. Shouldn't drawing this plane be almost the same as that? What's the only difference between S1 and S4? I actually have, like, this will get me this picture in the XY plane, or sorry, the XY plane. It's just when I move over, when I pick an X value and I start to draw this line segment, I don't want to be stuck on the ground. I actually want to come up, don't I? And I want to come up onto that plane, which means that when I pick an X and then pick my Y on the ground, those need to go up into the plane equation, which is going to put me up there. That means it has to satisfy that equation. So why don't I solve this for Z, and I will stop myself from being flattened out on the Z axis. I'll get rid of this 0 and replace that 0 with that equation solved for Z. Does it make sense that that would work? Let me write it down.
How would you know without the green picture?
How would I know what?
Like that can satisfy
Yeah,
if you wouldn't have moved it, I wouldn't have known.
you wouldn't have thought that it's just that projected. It's basically S1 kind of forced up into something. Yeah, like a shadow. Yeah, well, that's why I'm giving you 3D help here. Yeah.
Do we get 3D help on the test?
Well, see, the problem with this chapter, this section, the next ones, is that what we're going to do is we're going to say, hey, take this object that's sitting in three-dimensional space. Imagine there's a vector field, and then now we want to compute this thing called flux, which is basically the amount of flow into it and out of it. The book does not care whether or not you understand how to come up with the surface functions. They expect that you can. So I'm trying to help you because I understand this part is a hard part, is getting the surface functions. If you don't have these, you can't do any calculus. So just let's go through some more examples. You'll start to maybe feel more comfortable with it. Yeah? Okay, so this is going to be our fourth one, and it will be the same as this one, u and v. However, my z component is not flat anymore. It is that solved for z. So what happens if I solve that for z? What do I get? 2 minus 1, oh no, 2 minus 2/3 x minus 1/2 y. So that's what happens when I solve that for z. So I need every point that lives on this surface to satisfy that equation. So I need this to be 2 minus 2/3 what? U, right? Because u is the x. And then minus 1/2 y, but y for us is v. And then we will have the same restrictions, won't we? So what happens here is that it's actually really cool. I mean, when you start to really try and wrap your head around what's going on. You're picking a u, which gives you this direction, right? So you fix a u, and then you let v go between here and here, which will give you everything on this line, right? But as you draw this line, the z parts are no longer down on the ground. They're up on this surface, so it draws you that line on that plane. And then you just move u over a little bit more, and you draw another line and then map it up onto the plane, and you just wind up drawing the whole plane when it's all said and done. I hope that makes sense. Let's go for one more. We want to draw this cylinder. And I think I gave you a little more detail in yours, right? I gave you the equation of that cylinder, and I gave you some restrictions on the y. So how can we draw this cylinder? Well, how can we draw it with parametric? This is how we draw it with equations and inequalities, right? Draw me this cylinder. That's a cylinder, right? Radius of 1, and it opens out the y-axis because y is missing. But if I restrict y between 1 and 4, it's only going to draw it from 1 to 4 on the y. So this is a pretty well-defined way of drawing that cylinder, but I want to do it with a vector function. So let's say r of uv. Okay, good. I think I've already heard it. What is it? You're going to use sine and cosine. So if we just kind of look down, oh, wrong one. If we look down just from the y, looking down the y-axis, this is a bunch of circles, isn't it? All with the same radius. And I'm drawing them in the xz plane, like this. So I need to use my x and my z to draw me circles. And what's the radius of the circles I want to draw? 1. So I can just say cosine v sine v. That should draw me a circle, right? But what about the y? Make it u. That's your other variable. Make y u. And then give me some bounds on u and v. 0 to 2 pi, that's going to draw me full circles, right? And then y? What? U. Said v, y, u. Okay, so u is between where? 1 and 4. So it's kind of like, draw me a circle with this being 1. So it goes out and it draws this back circle first, right? And then you say, okay, draw me another circle, but this time let U be a little bit bigger than 1. So it draws me the next circle. And it just keeps doing that and doing that and doing that and doing that and doing that until it gets out to here, and then it stops. You're varying the y coordinate between 1 and 4, while your x and z's are going to be drawing circles. That was not too bad, right? Okay. Maybe we can get 2 in. Same picture, but this time I don't want the cylinder, I want the end cap of the cylinder. So I want this thing, this end cap.
Looks to me, like you said, it's the first example.
This is pretty much the first example we did.
Just with different
A different radius. Our radius is actually going to go from where to where on this one?
0 to 1.
0 to 1. But now we're not moving, right? We're stuck. Our y coordinate is stuck at what? 4. So for this one, I want my y coordinate to be stuck at 4. And I want my x and z to draw me the disk. So I have to control both the angle and the radius. So that's where I need the 2 variables. U cosine v, u sine v. Right? V will be between 0 and 2 pi, and u will be between 0 and 1. We might just keep cranking. This one's tricky. We have 3 surfaces here. We have the back disc, right? We have the cylinder, but it's not like a beer can, it's been sliced. And then we have this slice piece, which is like an ellipse, right? But it's like solid through. Do y'all see that? We have surface here, the bluish surface, and then the back surface. 3 of them. So let's start with the back surface. Do you all agree the back surface is going to be the easiest because we've done 2 of those now? Okay, now is this thing up against the... I think it's up against... I keep on going to the wrong one.
Yes.
It's up against the back. You can see that? Okay, so y is 0. So for that back surface, I think I can do that one, this back one right here. We'll call that S1. That's going to be R1 of UV, which equals, you tell me? U cosine V, y is 0, U sine V, V is between 0 to pi, right? And U's between 0 and 1. That should draw me that back surface. Right? Now, I gave you some additional information that's not up here. Let me look at it here. I gave you some information about that this right here is coming from x plus y minus z equals 2. That's a plane, right? So it's like a plane cut through my cylinder. All right, let's try and draw the blue cylinder right now. Let's try and draw this part right here. Not the plane, this part. How do we do this one? S2. S2. So think about as you draw that. You want...
We're going to be
Why is it going to be stopped by the plane?
Yeah, you basically want to draw circles, don't you? You want to draw circles like this, but you don't want to come all the way out.
What is the y component just be that?
The y component should be controlled by this. So let's do this. R2 of u v. You know what? I would like to offer example E, F, and G as a take-home small bonus. Let's say 5 points on one of your mini exams. That's like a half letter grade. All right? I want to see with what we've done and developed so far in class, can you go figure out the rest of these problems? All right? That sound like fun?
Yep.
Yes?
I'd like to take one.
You like what? Oh, you have to do them all in tournament. That's what I'm saying. You finish them up. You do
Oh,
E.
you said each must do each. I thought I was trying to.
No. Just like as a homework assignment to come in next class with. Have E, F, and G written out on paper, to turn in to me. All right? Don't do it on this. Just do it on separate paper.
Bring all three out, and then cut what each student takes one.
Yeah, no. Each of you does all three. Yeah. Okay? See how it goes. It's extra credit, but see if you can figure it out because I think it's an important concept. Well, you have to have it. You have to be able to do it. So, all right. Otherwise, I think we're done. And we will start getting into the calculus part of this next week. We're down to what? How many weeks now? 3?